All right, hi everyone. Let's start then. Okay, thank you for coming to the seminar. So today Parth is going to talk about his recent submission. We can talk about that. And pointer chasing in few rounds. Go ahead.
Thanks for the introduction. Thanks for coming. As Sepper said, I'll talk about pointer chasing. What is pointer chasing? It's a two-player communication problem. So the first player, who I'll call Alice, gets a function fa that maps from x to y. And the second player, Bob, gets a function that maps the other way. And we think of these as pointers, right? Each of the xi's is pointing to something, to one of the yi's, and each of the yi's is pointing to an xi. And the thing that we want to compute is the pointer chasing function, which starts at some v0, which will always fix to be x1. And then we sort of follow the arrows. So we follow the arrow, we get v1. And because of the way we set up the problem, there's only one arrow to follow every time. So you go to v2, v3, v4, v5, and so on and so forth. Okay, so we define the sequence, and then we want to ask what's the kth element of this. So more formally, Alice gets this function fa, Bob gets the function fp. We define this composition, which alternates between applying fa and fp. And then we want to compute f to the k of v0. The problem clear? You should think of k as going with n. People have studied the case where k is fixed as well, but at least in this talk, we'll think of k for now. Okay, so we will study the bounded down communication complexity of this problem. So what is bounded down? We'll focus on R rounds, and we'll enforce that Alice talks first. And then the players alternate who speaks for R rounds. And at the end of it, we will require that both of them know the answer to whatever problem we're trying to solve. Okay, so what is a k-round protocol for pointer chasing? It's pretty straightforward. Alice knows v0, so she can send fa of v0. And now both players know v1. Then Bob can send fp of v1. Okay? So they're literally just following the definition of the function and going back and forth. And you can do this for k rounds, and it's easy to see that at the end of this, they will both know v sub k. And the communication cost of this was k log n, right? Because we did k rounds, each time we were sending log n bits for the next pointer. That's it. What about if we had one fewer round? This is a series of really nice results. The first one I talked about was this deterministic lower bound of Nissan and Richterson. They showed that any deterministic k-1 round protocol needs omega n bits of communication.
This one, what should I think of k as? Because if I think of k as order n, like what you stated, then.
Yeah. You should think of k as something like n square root n, let's say. Okay. So I believe this result, I think, doesn't have any assumption on k other than like a bit smaller than n. But this second result, for example, which lower bounds the communication cost of randomized protocols by omega n over k, this assumes that k is at most square root n.
K is at most. And the first one, you said there's no assumption on k.
Yeah, I think that's true.
So, like, for example, if k were constant, is this still true?
Yes. When k is constant, even more is actually true. You can slightly go above omega n, but what am I saying? What am I saying? Yeah, something like n to the n times log of n iterated k times. Yeah, but I won't talk about those. Let's focus on these two. What's nice is that they're both optimal, okay, up to some log factors. The reason I mentioned 3 results over here for the randomized thing is that the first one is proving just a purely randomized lower bound. The second one is distributional. It finds some hard distribution for the problem. And the third one is reproving the second result, but it's doing it with new tools, which we'll use in this talk.
Is clear that it's optimal or? Is it
It's not
only
clear that
for
it's optimal. You need to do the protocol for this N over K is not trivial.
And what was in the account?
The deterministic one, you send the whole input. So it's optimal up to like log factors.
Oh, outlaw factor.
Yeah. More questions? Okay, what if you had even fewer rounds? Yes, this is the question that we asked today and we also answer today. So if you have K by 1000 rounds, okay, and this 1000 is for like making the proof easy to explain and write, it can be optimized slightly. So if you have K by 1000 rounds and your protocol is randomized, you need omega n bits. Yeah. There's one small caveat. I can only prove this lower bound for finding all of the pointers V1 through Vk. And I think this is some sort of technical artifact. It shouldn't be too hard to fix, but I don't know how to do it.
Previous N over K was for K minus 1 round or which?
Yeah, K minus 1. Is the result clear? So you should ask, why are we studying this? Okay, and so this is the real reason, right? It's nice and it's whatever. This is the practical reason that I tell other people. If you find communication lower bounds for pointer chasing, they give multi-pass streaming lower bounds for certain problems. Okay, and this implication is doing a lot of heavy lifting. Like you need to prove a lot more over here, like for variants of pointer chasing before you get non-trivial lower bounds for interesting problems. So I'm not going to state this as a theorem in our case because our result doesn't directly apply anything. Okay, but in principle, if you get better lower bounds for fewer rounds, they do imply better lower bounds on this side. And I'm not going to talk about this too much because I don't want to define what streaming is. Okay. So we're actually ready to move on to the proof. Yes.
Sorry, it's a question that would be better at the end, but for your main theorem, I assume that you think it would also be true if you had like 0.99K or something like this. Even though your theorem is for.
Yeah, I'm not sure how close to K I can get with my current proof idea.
But in terms of what you suspect is the.
Yeah,
truth,
what I suspect is truth, probably.
what would we get then? Is there a clean expression for what we should expect for K minus some functions? Not even clear what we should be.
I think the way I thought about it is that if I have n over k bits of communication, with the randomized protocol, I'm able to skip one round. Okay? And if I have roughly n bits of communication, I should expect to be able to skip roughly k rounds. Okay. And now in the middle, let's say I first fix the communication lower bound I want to prove. Okay, so let's say I have n over square root k communication or something. Then I should be able to skip square root k rounds, but I don't
No,
think.
it's just a guess, but like this n over k should be added in terms of how many rounds you'd be able to skip roughly.
Right.
Yeah.
Yeah, but then this is like, I don't think, at least this proof doesn't say anything about those things at all.
But just to look at the parameters, so then you're saying if you want a K minus T round protocol, it may record like the number will be T times n over K.
I think so.
So for example, like you mentioned, there is a randomized protocol that can like basically skip one round and N over K communication solved. Can it be like modified to even let's say skip 2 rounds that easy? Like I'm just trying to understand, is it to you obvious that for example, K minus 2, I shouldn't be able to get omega and lower bound or something?
Yeah, that's true. Like that protocol just works.
You can say the protocol must trigger out.
Yeah, I should just say that this. So the protocol is the following. You pick the players pick n over k point inputs at random, sort of on Alice's side or Bob's side, and they just send pointers at those points at the beginning. Okay, and now since you pick them at random, you have at every round you have a probability 1/k chance of landing on one of those inputs. And so over k rounds, you expect to hit one of those and skip one. All right, more questions? Yes.
This also may be better at the end, but you have a lower bound on all of V1 through VK.
Yes.
Can you relax this and say that you have similar lower bound for finding a large subsequence of these? Like if I want V1, V3, V5, all the odd index ones.
This should be possible as long as the sequence is very dense.
Okay.
Yeah, I think, yeah, I can probably answer this a bit better at the end. Okay. All right. Okay. So I'll give like a rough overview of the proof before we actually do some details. The proof is, as you would expect, working with a hard distribution. What is the distribution? We'll pick Alice's input to be a uniformly random bijection from X to Y. And Bob's input is the same, but from Y to X. And of course, why are we picking a hard distribution? Because Yau's minimax principle tells us that now we can assume the protocol is deterministic and only lower bound against those guys. Okay. So I'll do the proof in 3 steps. The first will be an argument against structured protocols, which I'll define in a minute. And then there'll be some sort of simulation which reduces a generic protocol to a structured protocol. And then ideally, I would repeat the first part and do it more carefully to account for the issues or the details of simulation. I'm not actually going to do this because we'll skip enough details that it will be impossible. But yeah, that's how it goes. So what's a structured protocol? It's what you would expect. It's a natural type of protocol where at each round, each player picks some subset of their inputs. So Alice, in this example, is picking x1 and xn. And all she communicates is those values and the pointers of those values. So in this diagram, I've sort of indicated the edges that she's communicated with black to mean that they're public information now. And now it's Bob's turn. He does something similar. Okay, he picks y1 and yn, and he sends those pointers. Okay? And now 2 rounds of communication have passed, and this is what the situation looks like in terms of public information. And so let's say you were to stop the protocol at this point and ask, okay, how many pointer steps have you chased? We start with V0, and we can follow that to V1, V2, and V3. And in this example, note that they got sort of lucky, like they did 2 rounds of communication, but they got 3 steps of pointer chase. Is the definition clear for structured protocol? In case it's not, it's here again, more commonly. In the ith round, the player who's speaking will pick some subset of their inputs and then send F at those inputs.
When Bob picks a subset, we try to make it overlap with FA of I or not?
Sure, you can. I mean, we're just restricting the type of communication, not like the strategy.
Yeah.
Questions? Okay, how do we measure the progress of these nice protocols? We define this guy QR, which counts how many of the pointers have you chased with evidence in some sense. Okay? So we're picking the maximum j such that v0 through vj minus 1 are all in the set of things that you fixed with your communication. So of course, if v0 is fixed, if f of v0 is fixed, you know v1. If f of v1 is fixed, you know v2, and so on and so forth. And I'm saying that QR is the number of pointers you know. And I want to point out that this guy is a random variable. The reason it's a random variable, even though our protocol is deterministic, is that we're running it on a distribution. So sort of the name of the game is to upper bound this random variable. I want to prove how we'll prove it is by induction. And we'll say that in each round, you cannot make too much progress. So I want to sort of do a visualization again of a round of communication. In the first round, Alice picks this subset. Presumably, she knows what she's doing, so she puts V0 in the subset. Bob picks his subset. Again, he puts V1 in. And now, this is the third round of communication. Alice has picked her set F3. Okay. And now imagine the situation from the public perspective. So there are some pointers that have been fixed based on the communication. Okay. But because we had this uniformly random bijection that we were running the protocol on, the pointer from V2 should be random. And it should be uniformly random over everything that's not been pointed to yet. Does that make sense? Because, for example, the pointer V1 already has some edge going in, right? So it certainly cannot have another input because the inputs are bijection.
That's just something
Yes.
that's problem I always have when there's a structured protocols. I can encode arbitrary bits in the message that I'm sending. And that will actually change as the underlying distribution. You know, so I need to look at our other edges, and based on that, decide to send this edge. So how do you say that these other edges are unique?
Yeah, no, that's a good question. So the way you argue about it is you sort of force or you assume that the point of VI will definitely be in your set. Okay. And then you only sort of, how do I say this?
Yeah, you know, my problem is this thing. So suppose Alice looks at V2 in her first round and decide that if V2 has an edge to the bottom, she's going to send an edge of some vertex V10. If V2 doesn't have that edge, she's going to send an edge of vertex V100. So now from public point of view, the fact that I got V10 also tells me that V2 doesn't have an edge to the bottom.
I agree. Yeah, so I guess what Sabra is trying to say is that the f of V2 is not independent of this set big F3, right? It depends, like in principle, since Alice knows what f of this guy is, she can encode her message based on that. How do I say this? Yeah. What you should think about is you can take an expectation over the message that she sends. Okay. So what is sort of the true distribution of V2? The true distribution of V2, like before this message was actually received in some way, is that it's uniform, right? Mm-hmm. And so what we want to say is that yeah, so pick up the set of inputs that sort of brought us here. Okay. And among those set of inputs, V2 is uniformly randomly distributed. And now Alice sends some message, okay, which is her message in the R+1th round. And sure, on specific values of that message, it's possible that V2 is not uniform and something strange happens. But in expectation over the message that she sends, V2 is random. And we are only interested in sort of bounding the progress of the algorithm in expectation.
Expectation. Expectation over the message it sends V2 is.
Well, it's an expectation over the input, and so that induces an expectation over the message.
I mean, is it close to random recursive or is that?
With this setup, where the protocol is super nice and structured, it is random, right? It's random over these guys, the remaining guys.
It's just very informal part, no? This is a structured protocol. It's a protocol that I don't still get it. You like what you're saying is that among the set of the inputs that are mapped then to this particular message, then this is random. Like if I have this message and 5 different inputs are mapped to it, any of those inputs have the same probabilities.
Sure.
Okay, so that I get. But my problem is that just because I'm communicating lines, or like arrows, doesn't mean that the inputs that are mapped to the same message are all the inputs that are only consistent with this text. If you kind of seem to assume that fix all these edges, all other inputs are available to you now. Is that the case or not?
Yes,
But
that is the
this
case.
doesn't need my protocol may do other things also. Even a structure, like I think your underlying assumption is that if I fix these 4 arrows, any input that is consistent with these arrows can be part of they can be mapped to this message.
Right. And you're saying that based on where we want points, you could pick a different set of arrows. And now the
Exactly,
same.
because the top edge went with there, some bottom edge cannot be part of it. We can take this offline, but
Yeah.
basically if your definition of a structured protocol is that any input that is consistent with these arrows is valid, then I agree with what you said.
Right.
And otherwise also it's unfair to us because a structured protocol is as strong as arbitrary protocol. Really, if you don't have something like this, I just encode messages by sending some random messages.
Yeah, I'm not seeing how to fix this right away, and I don't actually use this structured protocol in the actual proof, so it is offline is fine. Okay. Okay, so we have this questionable assumption that f of VQR is uniformly random, but if we have that, then let me use C to denote the size of everything that was fixed so far. Point is that with probability 1 minus the probability of hitting this guy, we know that QR plus 1 is only QR plus 1. The denominator turns up because that's the decrease in the size of the range. And we sort of need to focus on the situation where VQR plus 1 does land in one of these fixed pointers. And now something strange can happen, many steps can be skipped, so we need to do that. But also, just to sort of hone in on this part, we are going to assume that C is something like n divided by a larger constant. So you can see that this thing is going to be probability close to 1, like high constant. Okay. So how would we do the second part? We're going to break F into streaks. Okay. So what's a streak? A streak is a subset of fixed pointers such that you have the sequence W1 through WS, and each of them points to the next one. So how should you think of a streak? You should think of this as if my random pointer happens to land at the beginning of a streak, I'm going to skip forward by S steps. Or the game is going to skip forward by S steps. And now if I want to bound this expectation, then I again start with my fixed pointers. I break it up into streaks. And the actual sequence we're chasing is V0 up to VQR. So let's assume that that belongs to one of the streaks. And then what we said before is that with probability, this thing is slightly adapted now that we have more information about the set F. We miss F with this probability. Okay. And then we hit the ith streak with probability 1 over n minus L.
Sorry, what is L?
L is the number of streaks that we can partition.
Then it depends on the length of the probability that you hit it.
No, it doesn't.
Oh, I have to hit at the beginning.
Yeah, that's sort of the reason why we're working with this distribution on bijections. You cannot hit the streak in the middle. Does this make sense?
still don't see why you can't hit it in the middle.
Oh, you cannot hit it in the middle because we're actually fixing that S is in the fixed pointers, right? And we also said that, okay, Wi points to Wi plus 1 according to the actual pointer chasing function F. And I know that F is a composition of two bijections. So it's also a bijection. And so let's say Wi plus 1 already has something pointing to it according to F. Now it doesn't matter what you do, you cannot point anything to it. So you cannot hit the streak in the middle.
Either.
More questions?
So there shouldn't be like two n minus L because I could hit something that is in the beginning.
Say
Or
again.
I could, oh, sorry, but then I'll miss if I go outside, right? Because I can only enter from the first guys.
Yeah.
Okay.
And so we can collect this information and compute the expectation. There's one streak that's special. Imagine S0 was starting at some guy, then hitting V0 and going on up to VQR minus 1. And now you get super lucky and you happen to hit the beginning of the streak. You got like a cycle now. Since you got a cycle, you've solved the problem. So with probability 1 over n minus, this should be a 2 times n minus L in the denominator. So you get this K over this thing, you skip ahead, and the others are just depending on the length of the streams. And then you can add these numbers up, and it turns out to be less than 2. Okay, and what I told you in this proof is almost true. It's not exactly true. So imagine that you're Alice. Okay. You know FA of VQR. Okay. And so you know which streak it's going to hit, right? If it doesn't hit a streak, it doesn't hit a streak. But if it hits a streak, now you can kind of tailor your message or the indices that you fix to the fact that you hit this streak. So suppose that this streak that you hit also ends back on your side. Okay. Now you can extend it further, right? You don't need another round of communication for this because you know what's happening. And so you need to repeat this argument and treat it as some sort of geometric random variable. The point is that with probability close to 1, you miss entirely, right? You miss this fixed set entirely. You only gain one step, and you can't play again. Right? With the remaining probability, you do hit something in the thing, and you gain this quantity that we talked about before. And then you can play the game again. Right? Or at least I cannot rule out that Alice can play the game again. So you can think of this as a geometric process and show that the same sort of lower bound holds.
What is
C here is the number of fixed pointers.
what is L then?
L is the number of streaks in the fixed pointers.
C over L is larger than 1.
Yeah, C over L is larger than 1. But you sort of when you make this gain, you do it with probability L over n minus L. So you can multiply those two numbers together, and C is much more than the L. Okay. Like this is why it's not exactly clean to analyze it like a geometric random variable. You actually wanted to sum up the expectation explicitly. Oops. Okay. Questions about this? Okay, so that's the proof for the nice protocols. These slides were in the wrong order. This is supposed to be whatever. Okay, so now I'll show some version of the simulation argument, and this is based on this paper that I mentioned before of Mao, Yang, and Zhang. They reproved like this pointer chasing k-1 round lower bound using these ideas.
So, can you explain the K over L, like,
Yeah, the k over L is coming again from hitting the streak S0. Like S0 is special because it's the streak that the pointers were already in, right? V0 to VQR. So you happen to hit the beginning of that thing, and now you cycle around and you know all the pointers in some sense. So you just skip straight ahead to K. Okay. So let's talk about this simulation result. So what's the idea? You want to take a generic protocol now, okay, and you want to refine it into these type of protocols that we understand to some extent. So you want them to become protocols that either fix the pointer or leave it close to random. And before we do that, before we actually do this thing, I want to give you a viewpoint on how to think about communication protocols. So this is a completely natural way to do it, where you think of it as a tree, right? And on each node, you have the set of inputs that will reach this node of the protocol. And then you have a 0 edge and a 1 edge, leaving based on like what the next bit that the player who's talking will send. In this example, I've used the blue edges to indicate Alice's messages and the red edges to indicate Bob's messages. So yeah, so in this case, like you start with X and Y equal to all possible inputs. And actually for the rest of this talk, I'm going to forget my distribution of bijections. Okay, I'm going to talk instead about uniformly random functions. Okay, it makes a lot of the math here much simpler, but the ideas are very similar, the proof ideas. Okay, so yeah, so based on the message that you send, your set of inputs gets restricted to either x0y or x1y. And then you can repeat this process. Does this make sense? And I use blue edges for Alice's communication. So one round looks like a bunch of blue edges, then some red edges and blue edges. Okay, so how do we want to think about running pi on a random input? Okay, so the first viewpoint, which is more simplistic, is that you first pick a random input from your input distribution. And then you sort of follow the root to leaf path going down to where this input would end up. This path is not super accurate. But yeah, this makes sense, right? This is how a normal person would think about things. But if you want to prove lower bounds, you think about it a slightly different way. You start with these sort of analytical variables x and y, which are going to hold the set of possible inputs. So you start with just all possible inputs. And then you make random choices according to your distribution. So for us, the distribution was flat, right? It was uniform over something. So we can just make our distribution, our choice based on the size of the sets. So with probability x0 by x, I'm going to go left. With probability x1 by x, I'm going to go right. And then I can repeat this, right, on each node of the protocol. And then at the leaf, I'm going to arrive at some new set xy of inputs, right? And this is all the inputs that would have reached this leaf. And at this point, I pick a random input. So at the end, the distribution you got is the same. Right? But in one case, you pick the input at the beginning, and then you did the protocol. And here we're doing some sort of simulation, and we do it at the end, we pick this. So why is this second viewpoint helpful? The point is that once we reach a leaf node, pi being a deterministic protocol has fixed its output. Okay? So I got some set of inputs that are going to come here. And then if the correct output on this leaf is sufficiently random, right? I had this set xy, I'm going to pick a random input from there and say, what is the output here? If the set was sufficiently spread out or whatever, doing some weird things, then the output would be random and pi is wrong. Does this make sense? Okay. What we're going to do is refine the protocol slightly, okay, to get this structure that we need. So imagine that you start with, you're at some node xy, okay, which has some set of inputs xy coming to it. And now Alice sends a bit, okay? And it's a weird bit, like it's splitting the input up in some strange way. I have no idea what she's doing. And it makes my input unstructured. It doesn't have this fixed indices and random indices sort of structure. So what we will do is split the input up further, okay, into some set x00 up to x0m. Okay, and we'll force these guys to be structured. And so in some sense, when we're doing this simulation in our head, right, of a random input on the protocol, we're adding some extra steps. We're just saying, I was at x0, y, I'm going to divide it further and pick one of these at random. And then I'm going to continue the protocol. And now you might ask, oh, well, the protocol was expecting something from x0, y or something. But since these are subsets of that guy, the protocol can deal with all of those guys and, define new partitions of these. So we can sort of continue.
Wait, can you do it with an actual protocol even, or is this another thing?
I think you can do it with an actual protocol.
Like you just
It
take
won't,
that
yeah, it wouldn't look good. It would, because you wouldn't be explicitly communicating the indices that you're doing. You need some good encoding of it, but
like that purple tree now, it does it have two edges or?
like this out degree
have a
too.
very large
Yeah, it has really large out degree, but that's
The tree, it won't be. Like if I turn that large out degree into an actual binary tree,
Right.
that's an actual protocol function.
I think so.
Wait, but then those blue ones
Mhm.
here, just to go back, right, they're also mapping to other subsets. So from here on, there's no more purple, you just do purple.
No. There will be. I
You
do
do
purple
purple
after every
everywhere.
step, everywhere. Yeah.
Okay,
like-
but then does x01 here would be like x00, like 001, right?
Yeah. I sort of ignore the superscripts. At this point, I'm just going to say, oh, x becomes this guy. So.
Yeah.
Okay. What's the point of doing this? Okay. The point is that the leaves are now structured. Okay. Like this sort of thing. And then in principle, it should be easier for us to argue that the output on a leaf is random. Okay. How do we actually do this? So this is a primitive of this paper of Kuspidasi Watson. They said that if I'm given this set X, okay, now it lives in n to the j. So it has j coordinates. Each of them is taking values in 1 through n. I can partition this guy into sets x1 through xm and index sets these guys, such that the first thing is that xi is constant on ii. Okay, that's what you would expect. Some of the indices are fixed, and xi on the remaining guys is random. I should have put quotes on this because it's not truly random. And with the picture, I just want to indicate this. It will look something like this. You had this set x, okay, which originally was coming from some communication protocol, but now you can think about it as purely as a set of inputs, okay, or as a set of vectors. And I'm splitting this up into these guys, such that on some coordinates it's fixed to be some value, on the others it's close to random. So you should ask, what do I mean by random? And the measure that I will use for randomness is min entropy. Okay. So what's the min entropy? I have some variable x, okay, and I take all possible outcomes for this variable. I look at the one that has the largest probability, and I take log of 1 over that. And if you've seen this expression, like at least you've seen the right side of this expression before, if you take an average over alpha instead of the min, that's the Shannon entropy. One of the ways I'll use this min entropy is as a potential function. Okay, so we call this the deviation of a random variable, which is supported on n to the j. And I want to point out that this thing j log n is the maximum possible value that the min entropy could take if x is supported on n to the j, and that's the actual min entropy. So this is saying, okay, how far am I from the maximum? And certainly this quantity is at least 0. Okay? I can be no better than the maximum. And so this would serve as our potential function for some analysis.
Is it the equivalent of k divergence from uniform?
Yeah. Okay. And then how we'll actually apply this min entropy to say something is random is to call it gamma dense. Okay. So we'll say that x, which is a subset of n to the j, is gamma dense if when I pick any subset I of indices, then the min entropy of xi is close to what it should be. Okay. With this correction factor of gamma. Okay, so I log n would have been the most possible, and with gamma some sort of slack. And I want this for all subsets. Yeah.
So good, like a dense set is when gamma is one, basically.
Yeah, super dense set is when gamma is 1.
And what will like reasonable values will be like in your program?
For us, gamma will be 1 minus 1 by log n. Okay. I want to say a little bit like about the history, like when Goose, Patasi, and Watson were using this sort of thing, they were doing it for these query to communication lifting things. They had gamma equal to a constant. I think one of the sort of, I don't know, big innovations in the paper of Mao Yang and Zhang is that you can set gamma to these things and then make arguments using this directly in the communication world. So like even this choice of gamma is not new. Okay, let's do some examples to make sure the definitions are sitting in our head. So let's say x is uniformly random, x1 is uniformly random from smaller set than n. Everything else is truly uniform. Okay. So because our definition is focusing on every single block of indices, in particular, I can look at x1 and say, well, the min entropy of this guy is log n by 2 minus 1. This is like barely less than gamma log n. So by our definition, this x is not gamma dense. Let's look at another example. This definition also captures sort of correlation. Okay, so let's say you had x1, which was truly uniform, and x2, which is a slight modification of x1, but it's not independent at all. And then the others are truly uniform as well and independent. So then you can focus on the first two indices, and their min entropy is log n. And this is again significantly less than 2 gamma log n. So this is also not gamma dense. So I can now state the density restoring partitions lemma more formally. We have these two conditions again, that xi on ii is fixed and xi on the unfixed part is gamma dense. Okay? And then we have this weird thing which is saying something about the potential. So what is this potential thing? It's saying that how you should think of it is the following. You're saying that I fixed I sub I things, right? I sort of restricted my universe to where these I sub I things are fixed to be some value. Okay. So sort of the maximum possible min entropy should drop by I sub I, right?
Can you repeat that?
Yeah, the maximum possible min entropy should drop by I sub I. Like, you know, what the viewpoint is here, we want to think of this guy as not even being supported on J anymore. Okay? Because on everything in J, it's not really random, right? On things in I sub I, it's fixed. It's not a random variable. So I should think about it as a variable on J minus I sub I. And so, you know, the requirements for it to be random should be reduced further, right? Because the number of indices fell. So this is numerically what happens. You gain this minus, or in the density, you gain I sub I log n, right? And then there's like a slight loss because of this gamma thing, right? Because the thing that we fixed had some probability which was larger than what we hoped. And so this is, yes.
So if I'm thinking of the structured protocols, for example, then it's like after one round is I sub I, basically the obvious that correspond to the edges that Allison and J minus and sub I before she has an communicated so forth. That's sort of the
Exactly.
idea. But for gender protocols, what we're trying to do is like look at this sort of tree structure and somehow decompose it this way and then you're able to generalize.
Yeah, that's exactly. Okay. Yeah, so does this make sense?
Is this kind of where you were hinting at in terms of the whole uniformly random kind of argument? That
Yeah, exactly,
so
exactly.
that density is what.
Exactly. You have this gamma density instead of like being truly uniform.
That makes.
So now I can tell you what the actual simulation is. And we're going to zoom in on one node of the protocol. Okay. So, and we're going to assume we're Alice. Okay. So Alice's input is uniformly random over some set X. And now she sends a bit which separates it into X0 and X1. And now we add a bunch of steps for the simulation. Before that, I want to say what happens to the potential. Okay. So I don't know what Alice's bit was about, right? I don't know this sort of, how do I say it? This previous thing that I said that, oh, this set X is now fixed on a bunch of indices, and so its universe should be reduced. This sort of thing doesn't apply here, right? Because Alice could be doing whatever, she had some arbitrary partition. So the density or the deficiency just increases. Like it just gets worse. And what we will do is follow the idea of picking a random input that we had before. We're just going to pick I with probability proportional to its size and set H to be Xi. This part is the same as like before, as in we're not doing anything fancy yet. And I want to point out that the expectation of the deficiency gain is at most 1, okay? Because this is just the entropy of 1 bit. And then the second step is to run these density restoring partitions on the new set that we got. And we obtain this partition and this set of indices. And again, we do what's natural. We pick one of those based on its size, and we set X to be Xi. So again, this is just a refinement of the existing protocol. We're not changing the distribution in any way. And this gives us a deficiency drop of roughly this much. Okay. And what I want to point out is that the deficiency drop is proportional to I sub I, which is the number of indices that were fixed if I pick the ith guy. And so what is the implication of a low communication protocol? We know that each bit of communication increases its potential by 1. And we know that each run of these density restoring partitions decreases the potential by the coordinates that were fixed. And so in expectation, the number of fixed coordinates is at most the number of bits of communication.
What about the original value of the?
Initially, the deficiency is 0 because we started with a uniformly random.
Not for you though, so in your case.
Good. Yeah.
I see in a truly uniform distribution, it is 0.
Yes. So, yeah. Okay. Does this kind of make sense? So the sketch of the lower bound then is that I'm going to take a round of pi. Now, a round of pi is all the messages that Alice sent in the first round, for example. And corresponding to it, there'll be one round of the simulation, right? With all these density restoring partitions, picking the random thing and continue. And now imagine we paused at the end of the first round, okay? And we have some distribution of nodes in the tree that we're at. And then on these nodes in expectation, I can upper bound QR. Okay? And the argument is similar to what we did before, but again, it's more finicky because now we only have this gamma density as opposed to. But it'll use the same fact that the number of fixed indices is not too much. And as Sabra pointed out, like this is not true for bijection. Like this whole time I was talking about truly uniformly random functions to start with. Because the setup is completely different. The number of possible inputs is only n factorial. And so you would start with a different maximal value of the min entropy. And then after you fix things, it doesn't become n to the j, it becomes j factorial. And so you need to modify all of these definitions, like change the potential, change what gamma dense is, and all these things. And this is, let's say this, if you think about it for 10 minutes, you'd come up with these exact numbers. And after that, you just plug these new numbers into the proof, right? And it just works. Like, there's nothing to change. Okay. So you might ask, okay, what do you want to do next? It would be nice to prove this lower bound for piece, okay? And you want to extend this to gadgets, right? This connection that I mentioned to streaming, this raw pointer chasing doesn't seem to give super nice lower bounds, or like it gives lower bounds, but not for super interesting problems. If you want actually interesting graph problems or something to get lower bounds for, you have these versions of pointer chasing which attach a gadget before you get a pointer. The players have to solve some communication task to get one pointer. It would be nice to extend these lower bounds there. That's all I want to say. Thanks.
For example, your future direction extending to gadgets, what are some of like the immediate challenges that need to be handled? That's it.
Good. So what you would need to do is say something like, you know, you do see bits of communication in some round or something. And what we were doing is that we're translating that to the C indices that were fixed at this point. So now you would need some translation of, I did see bits of communication. Let's say my gadget is set intersection. Okay, it's a popular list. So then you would need to say that, I did see bits of communication, and the set intersection instances, some of them you solved exactly correctly, C of them you solved exactly correctly, and the rest are random with respect to this gamma density type thing. So these things are known for regular entropy, right? You have C bits of communication, you had a bunch of set intersection instances. You could say that C of them, or C divided by N of them, I solved really nicely. Good job on that. And then the others, they have to be roughly random with respect to TBD or some distance. Okay? It's not clear how to extend this thing to say that they're gamma dense, like the ones that I didn't solve.
So can you combine these two things? So use information complexity to say that on a random set intersection instance, I reveal the small of one bit. But for you, you have to handle the correlation between the instances, basically. Yes. You're handling like this mean entropy, this blockwise mean entropy thing handles the correlation between multiple indices, but I see. And information complexity doesn't give you those type of guarantees.
Yeah, I don't think it does. No, because I think the simplest thing you can say is with these set intersection type lower bounds, you have the information you have about this whole set of inputs is only so much.
Yeah.
And so the average information you have about one of them is only so much. And so there's a set of them which you have no information about. But now I don't think I know how to say there's a set of them such that for all of this together, I have low information. So,
Maybe it does, no? Because they're direct products for set disjoint as. So is this a direct product question? You simultaneously cannot solve this large subset.
yes, I think so.
Like the whole point will be to black box the use of information complexity over set disjointness, and then we get some guarantee in it, and then we pass it into an entropy. Any other question?
Yes.
Is there, this is maybe a bit of a out there question, but is there any connection with these bounded round protocols for punctual leasing and bounded depth Boolean circuits?
Yeah, so
Does your work have anything interesting to say?
it doesn't, because the paper that I briefly mentioned, the Nissan and Vigdusson paper, they showed this, they used this connection of Kashmir-Vigdusson games and said that these k-1 on lower bounds for deterministic protocols imply some circuit, monotone circuit lower bounds, right? But the randomized communication complexity plays no role there, as far as I know. So it's sort of, how do I say it? For a while, it was just an academic question to think about the randomized communication complexity. More recently, there's like these streaming lower bounds and all these things. But
Right, let's find Parth again.